Now, get the slideshow set up from current slide, though I won't be using that yet. We'll be starting on the whiteboard. And the whiteboard taskbar is in the way, so let me move it. And also adjust the whiteboard what I can. Okay, there we go. All right, any other questions, issues, concerns? Let me see, 12 people here so far. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Someone's here that I don't have marked. Let me see who that is. Esther's trying to get in. Okay, nothing popped up to tell me that, so if y'all can tell that someone is trying to get in, please let me know, because when I have all this open, it sometimes doesn't respond the way it's supposed to. So Esther's here now. So now we should have 12 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Got it. Okay. Okay, I'll close this off for now. Any questions, issues, concerns, anything such as that before we get started today? All right. I think I'll hold off and repeat what I said about the test when we finish the chapter, because that basically is going to be a good time to do that, and at that point more people may be in. I won't have to repeat it. So if there are no more questions, this new headset manages to get caught just about every way, because it's not wireless. Any way it can possibly get caught, it seems to find new avenues to do so. Okay. All right. I'll try holding it in my lap and see if that works. Now, yesterday in one of my classes, I wasn't hearing anything from any student for quite a while, and finally I said, "Can you hear me?" And someone's picture came on, and I mouthed the words, and he said no, he could not hear me. So I did fiddle around with the button, and it came back. So if something like that happens, if you can, some of you, I think maybe in some of my classes anyway, can write on my whiteboard. If you can, write on my whiteboard and say, "We can't hear you," or something like that. So that'll alert me to the fact something's gone wrong. This is a great device. It's been very helpful, but it does have its flaws. Okay, so let's do example 7 if there are no questions on page 369, chapter 5, integration, 5.8, inverse trigonometric functions integration, and example 7. It says, find as many of the following integrals as you can using the formulas and techniques you have studied so far in the text. Okay, and here's the first one, 7a. Okay, is the integral of dx, and it seems like we did this one, not in this place but somewhere else, over x log x. Didn't we do that? I swear it looks so familiar. I don't see it. Maybe it was back in the log chapter. Okay, now how would you proceed on this? Anybody? No ideas? Make up something. Okay, where I usually go, now let me make sure, can y'all still hear me? Somebody, can you hear me? Yes. Okay, good, thank you. That happened yesterday. I didn't want it to happen again today. Okay, so what is messy about this? Well, the main thing that's messy is everything's in the denominator pretty much. Well, what's the sort of the most complicated thing in the denominator? That would be the log x. That's where I would choose to do my u substitution. I feel like a second grader in my writing here. Let u equal log x. And for those of you who have looked at the test so far, this is what's new about Word, and I think they've just gotten so much worse than it was. I grew up word processing with WordPerfect, which is a fantastic program. Always has been, okay? It's not used very much anymore. It was the top of the line. Word came in and crowded everybody else out of the market. But WordPerfect's equation editor is so fantastically easy to work and gives you exactly what you want. This Word one, it's awful, okay? I have to literally do the same thing I'm doing here. Anything like an integral or anything that's complicated like this, I have to do it on a screen, and then it interprets what that means. And you see my lousy writing, a lot of interpretations don't get right. So I had to redo many of those equations that you see on that test several times trying to get it to be what I wanted it to be. And then I found out that some of you can't even read the thing. So that's why I had to do it into a PDF. So anyway, there's our let. Anytime you have a let, follow it with a then. Okay, and what's the then here? What? I didn't do that. The pen decided to do that. Okay, then the du. If you figured out what u is, you got to figure out what du is. And what would bu be? What is the derivative of log x? Somebody can answer that one. Anybody? 1 over x dx. Perfect. Okay. Always have a d's with the d's. Okay. The dx on this side if there's a du on the other side. Okay. Now that's looking much better, because what do we have here? A 1 over x dx. And then this is your, and 1 over x dx is du, and this is your u. So what do we have here? You have the integral of du, that's 1 over x dx, over u. And I think all of you should be able to give me what that is. Anybody? Undoes what we just did here. This we're taking the derivative. Here we're going the other way. What is du over u? Natural log of absolute value u. You're absolutely right. Now you need to put the absolute value bars. Now that's beginning to look like a 4. It's not. That's a u. Now you go back and plug in what u is, or u are, okay, and that's log x. So basically this is, I should have put my c there, but I didn't. I'm going to put it here. Whoa, here comes Daniel. Okay, now that one did show up here. So let me get Daniel in the class. Okay. Now, don't know why this popped into my head at this time, but let me go on and get this done. So that'd be log of the absolute value of what u is, and u is, or u are, log x. And you could have put it, you should have put it on the previous step too, I just forgot to, plus c, plus the constant of integration. All right. Any questions on that? Now here's what popped in my head when I looked at my grade book again. Someone asked in one of my classes, I don't remember if it was this class, it seems like it was this class, um, maybe a week or two ago, when is it that you have to complete your payments by? And at that time I said I did not know. I still do not know. Now they may have sent an email recently. This morning my entire office hours were spent trying to develop and started typing up a lab for this afternoon's class. So I didn't get to check emails like I had wanted to this morning. So I don't know if anything new has come out. But I know that they have done the no-show report and they're still trying to clean that up. And usually sometimes shortly after the no-show report, they do go in and do this thing, purging all non-paid students. So hopefully you're going to get something before they tell you that, but there's no guarantee they're going to do that. If we were on campus, probably something would come in our boxes about it. We're at home and it may be our e-boxes. And like I said, I didn't get to check email this morning. So let me just say, good idea to get that payment done as soon as possible. If you do get removed from the class, then you have to go through a few hoops. They're not really all that bad of hoops, but you still have to spend your time and someone else's time, trying to get back into the class. And usually they let people back in, but it's just a waste of time and energy on all your parts. So try to get the payments completed as soon as you can. Okay, just wanted to throw that out there because it had been asked and I hadn't addressed it since because I still haven't seen anything, but I thought it seems like it's coming closer. All right, that is the first part, the A part of example 7, and if you look at the solution in your text, that's exactly what they get. The log of log x, absolute value of log x, plus c. All right. Now it's only because some of these may take more time and space than what we have. Does anyone need this to be up there any longer, or can I erase it? Okay, since I'm not hearing anyone screaming, I'll clear the drawing. Let's do the B part. What about this one? Now that looks a little similar, but let's see what it is. The antiderivative, or the integral of, indefinite integral, of log x. Boy, they seem to be stuck on that, don't they? Over x dx. All right. Now, I don't know about you, but it seems like to me probably exactly what we did before, at least the first part of it, should be our first guess here. Anyone want to suggest what that should be? I'll write down the let because you usually begin with the let if you're doing a use substitution. And I think that may be the way to go here. What would you let u be here? I would say that same thing, log x. Let's see what happens with it though. It may not be as pretty a picture as the last one was, though this looks more like a simpler thing. Always follow the let by then. This is ugly writing. I think most second graders would be as embarrassed to write this way, okay? What would your du be? Same as before, anyone remember? Derivative of log x is 1 over x dx. Alright, well now you got a u times du. U is log x, and 1 over x dx is du. So this substitution is going to be the integral of u du. And that's actually easier than the last time. Because what is that? antiderivative. Please, somebody knows this one, I'm sure. What is it? Power rule. What would that be? Increase the exponent by 1. Right now it's a 1. Increase by 1. It becomes a 2. But then you divide by that new exponent. Divided by 2. And now we put in our plus c. Forgot to do it last time. I'll put it in the right place this time. Now we go back and do our, figure out what the u is. It's log x. So this will be, let me go and put the 1/2 in front. That's an ugly 1 on top. Let me see if I can clean that up a little bit. Well, now the eraser doesn't seem to want to erase. Okay, I'll put the 1/2 there, and then in parentheses do my log x. Now this one you don't have to put in absolute value bars, because in your problem it wasn't absolute value bars. So you're assuming they gave you a problem that was, what do they call it, well posed. So your x's aren't going to be any values that wouldn't make any sense, otherwise you couldn't do the integration. So we'll leave it just log x, but that's squared. U is squared. So all log x squared. That's why I put it in parentheses. I guess you could say log 2 squared x. That's a ambiguous looking thing. I think it's easier to do that. And then you just put your plus c, and that should be it. Let's see how they did on theirs. They put it over 2, which is fine. I just did 1/2 log x in parentheses squared plus c. All right. Let's do the next one. I'm not going to clear the screen. This is the c part, and this is the integral of log x. Boy, this is looking even simpler, isn't it? Log x dx. Is it simpler? What do you think? Guess what? You don't have a u substitution you can make here. And between you, me, and the fence post, I do not know of any function that when you take a derivative, you get log x. Okay? None whatsoever. Okay? And what's more, even if you did, whoa, here comes iPhone. Okay? I'm guessing that's James. So let's see if that's James. James Mullins. Okay, is that James Mullins just coming in? All right, good deal. Thanks. Okay. All right. Seems to be some background noise there. Okay. Guess what? Even though that's the simplest looking of these three, no way you can do it, because there is no function whose derivative is log x. So the antiderivative of log x, as far as I know, doesn't exist. And it says you cannot find this integral using the techniques you have studied so far. And that is the end of 5.8. So homework exercises here would be any of the odds 3 through 21. They're all on Calc Chat, and 5 is at Calc View. Any of the odds 23 to 33, they're all at Calc Chat. 23 is at Calc View. Any of the odds either 35 through 41, they're all at Calc Chat. 35 is at Calc View. Either 43 or 45, they're both at Calc Chat. 45 is at Calc View. Either 47 or 49, both at Calc Chat. 47 is at Calc View. You can explore doing 51 or 53. They should be at Calc Chat. There's a slope field problem that I think we talked about before, the number 55. You can either do it or just see what how Chat did it. you'll be doing something like that probably if and when you ever get to differential equations. The text I'm using now does use these slope fields, so you can go on and get introduced to it here. Then either 57 or 59, they're both located at calcchat.com. 61's at calcchat. Either 63 or 65, they're both at calcchat, with 63 being at calcview. 67 is at calcchat, as is 69. Then 71 is a true-false. It should be at calcchat. And verifying integration rules, 73 or 75 should both be at calcchat. Then there's something that goes back to numerical integration, basically using the midpoint rule, which you studied, oh boy, back at the very beginning of this chapter. It seems like somewhere back there. And that's it for 5.8. There is a little article they mention at the bottom of the exercises that if you are interested in pursuing something like that, there's a source. You can look into it and see if that might be a paper that you'd be interested in. All right, now we move to 5.9. And again, this is not going to be something that I'm testing you on. If you've looked at your test, you'll see it's not there. This is 5.9 here. What I'm going to do is just do as quickly as I can. Whoops, here's Anita coming in. So let me get Anita here. Anita's here. Turned out to be a pretty good class size today. Way to go, team. All right. Anita, if you're in here yet, we just finished the last example in 5.8 and gave you homework exercises there. We're now just going to look at 5.9, okay, at 5.9, and it's just going to be a slideshow. In case you ever need this, you'll have been exposed to it, and you'll basically know where to go to look it up, okay? 5.9 is dealing with hyperbolic functions, which have never been my favorite. And I remember doing them in calculus, probably 2 in college, and except for when I've taught this again, I don't think I've ever used them in any application whatsoever. Okay, that's not saying there aren't applications that would use them, that you could deal with them, but as we'll see, to me it seems like they just made up a new function for some reason. And yeah, I can conceive of some cases it may be useful, but by and large, you can do everything you can do without making up the new function. And I'll explain that in a minute. And here comes Joy. So let me get Joy here. Okay. All right. Good attendance today. We're only missing Houston, Amina, and LaRon. Angelica Webb we haven't seen from the beginning, so I don't know if she's going to be here or not. Hopefully maybe one to three of those others will be coming in. Hope so. So let's move on to hyperbolic functions. Again, you're not responsible for this on the test, but if your field of study uses these extensively, at least you'll be exposed to them. Okay, here we go. Well, here we don't go. For some reason, I have to click on the screen before it's going to advance. There it is. The objective of this section, which you're not going to do very strenuously, develop the properties of hyperbolic functions, and they do have some. Differentiate and integrate hyperbolic functions, which you can do. Develop properties of inverse hyperbolic functions, which really gets to be sort of a pain. And then differentiate and integrate functions involving inverse hyperbolic functions. Okay, so let's move on. You'll look at a special class of exponential functions. Now there's the key. These are exponential functions. And what are the easiest functions in the world to deal with? Exponential functions. So why not just deal with them as exponentials rather than creating a whole new set of functions? But that's my little pet peeve. The name hyperbolic function arose from comparison of the area of a semicircular region as shown in this figure right here, with the area of a region underneath a hyperbola. That's where the name hyperbolic came from. Of all the years I've ever studied and taught these things, I think that's the first time, this book is the first time that's given at least a little indication of where the name came from. So the area under a semicircle here that you can get by integrating y is equal to the square root of 1 minus x squared, and integrate that, and this is a radius from 0 to 1, radius 1, circle of radius 1, okay? And the whole circle would be x squared plus y squared equal 1. You're only doing the top half of that, so that's why it's the positive square root when you solve for y. Subtract x from both sides, you have 1 minus x squared. Take the square root, but only take the positive square root, and that gives you this. Okay, the hyperbola that is expressed this way, y is equal to the square root of 1 plus x squared, happens to be a hyperbola, and you get that by minus x squared plus y squared is equal to 1. And again, we're only going to do the upper portion of that. This hyperbola, like all hyperbolas, will have a mirror image down here. We're not dealing with that, only the upper. So the positive square root here too. Same thing, add x squared to both sides, take the square root of y, and you get square root of 1 plus x squared. The area under that, I guess, is what they're suggesting is related to the area here. Now, it doesn't seem like they could be the same, and they're not, okay? This has greater area than that because they have the same max. The max here is the min there. This gets bigger, this gets smaller. So, okay. It's a comparison, and that's all it is. The integral for the semicircular region involves an inverse trigonometric function, a circular function, and that would be the integral from minus 1 to 1 of this thing. Now, I would not do it that way, okay? I would go back here and say the integral from 0 to 1 of this and then double it. That's so much easier to do than going from minus 1 to 1. You can do it either way, but it's twice the area from 0 to 1. But that's okay. That's not what they're getting at here. Okay? And this is what they get, and that is involves also an inverse sine. Okay? And that's about, it's equal to pi halves, which is about 1.57, blah, blah, blah. Okay, that's the area under that semicircle. Okay. Now, if you think about it, the area of an entire circle would be pi r squared, and this is half of that, so it would be pi, and r is 1, so that would be 1/2. So you could do this without doing integration. Okay, never mind. The integral under the hyperbolic region involves the inverse hyperbolic function. Well, we haven't even decided what that is yet, but that is supposedly then the, and that's about 2.296. Doesn't look like it's anywhere close to that one. Okay, no relationship there. It's one of many ways in which the hyperbolic functions are similar to trigonometric functions. Okay, if you call that similar, okay, yeah, the forms are somewhat similar. Okay, and that's why they're given the names SIN and CON. Sometimes they'll pronounce it sinh, even though there's not a C in there, where cosine, hyperbolic cosine would be cosh. That is how it would look. Inverse hyperbolic tangent, there's no way to pronounce the H there, so they just say inverse hyperbolic tangent. They don't usually mess with secants, cosecants, and cotangents. At least I hope they don't. Okay, that gets really messy. Okay, so here's the definition, and this is why I see no reason for them. Exponential functions are so easy to work with. So if you're dealing with that, this is how they define the hyperbolic sign. E to the x minus e to the minus x divided by 2. Now that doesn't look at all like what we were just looking at, but that's the definition of a hyperbolic sign. Hyperbolic cosine would be e to the x plus e to the minus x, not minus but plus, over 2. Hyperbolic tangent would just be the inverse, it would be the ratio of hyperbolic sine to hyperbolic cosine. There's another way they're similar to trig functions. If you did that, it would just be e to the minus x, e to the x minus e to the minus x over e to the x plus e to the minus x. You could write it that way rather than writing this. Okay. Hyperbolic cosecant of x is just the inverse of this, 2 over e to the x minus e to the minus x. Now, there x can't be 0 just like it can't with cosecants, because secants of or hyperbolic sine of x is 0, so you can't have of 0 is 0. Hyperbolic cosecant is the inverse of this one, and if you look at that, that can never be 0. Okay, if you look at this one, this is why this can be 0 at 0. This would be 1 minus 1 is 0. So that's why you can't allow x to be 0. But over here, that numerator, e to the x is always positive, e to the minus x is always positive. Add them together, divide by 2, still positive. And inverse hyperbolic cotangent of x is just cosh over sinh, or 1 over tangent, hyperbolic tangent, or e to the x plus e to the minus x over e to the x minus e to the minus x. Again, you can express them always in exponentials, and they're so much easier to work with. Okay. Here are the graphs of those 6 hyperbolic functions. Now here, they no longer look at all like trig functions. Okay. The hyperbolic sine starts negative, goes up here, and becomes positive. Now right in here, that looks a lot like a trig function would look, but it doesn't come up here and turn over, or go down here and turn back up. It doesn't do that. It keeps going south. So these are not periodic functions. Okay, none of them are periodic functions. Here's hyperbolic cosine. It basically looks just like a hyperbola. In fact, it's fairly close to that. And by the way, if you haven't figured it out, this line here is, oops, my internet connection says it's unstable. I'm going to wait a minute and let that go off. Did I get gargly in there, or was I okay talking when the internet connection came on? Okay, I'm assuming it's okay. So here's e to the x over 2, 1/2 e to the x, that intersects at 1/2 here, not at 1 where e to the x would. That's how it looks. And e to the minus x would have come down like this, but because it's minus, it flips and goes down here. So you see, when this part is going to 0, this one takes over. And when this part is going to 0, that one takes over. So there's your hyperbolic secant. And again, so much easier in my mind to deal with the exponential functions than the hyperbolics. Hyperbolic cosine is this way. Here's e to the x over 2. Here's e to the minus x over 2. When you add those two together, this takes over in that direction, this takes over in that direction. Okay. Now, the hyperbolic tangent function, which I can't think of any time I ever used it. Frankly, to me, it looks a lot like an inverse tangent function. It's just that the limits are in the wrong place. Inverse tangent function goes down to minus pi halves and plus pi halves, but it looks very similar to that. So what that's used for beats me. Okay. This is your hyperbolic cotangent then. Obviously not defined at 0. So it's basically a hyperbola here. Not quite a hyperbola maybe, but awfully close to it. It looks similar to that. It has 2 different, well, that could still be hyperbola. Your hyperbolic Secant is this looking thing. Nothing like a secant function, okay? A hyperbolic cosecant is like this. Again, because sine like tangent is 0 at 0, this is hyperbolic cosecant and hyperbolic cotangent are not defined at 0. And this is indeed, looks just like a hyperbola. I'm sure that is a hyperbola, okay? Similarity just can't be any more different. Okay. Note that the graph of hyperbolic sine x can be obtained by adding the corresponding y coordinates of the exponential functions 1/2 e to the x and minus 1/2 e to the minus x. Likewise, hyperbolic cosine, same deal, adding this and that, okay, that we already pointed that out on the graph. Many of the trigonometric identities have corresponding hyperbolic identities. Corresponding but not quite the same. And that's what makes it so confusing. If you start thinking trig functions, you're going to mess up because of signs. Now in some places they're the same, in some places they're not the same. Okay, like here, sine squared x plus cosine squared x is equal to 1. Here, hyperbolic cosine x minus hyperbolic sine squared x, that's equal to 1. Okay, I guess those are corresponding, but they're not the same. They're just enough different to cause you to make errors, okay? So here are some of those hyperbolic identities. Again, if you ever need them, you don't need them for this class, okay? Here is the difference. Here, for tangents and secants, hyperbolic tangents, hyperbolic secants, it's a sum. Whereas that's different from what it is for sines and cosines, you know, for trig functions. And then this is the difference again, which is fairly similar to the difference you have in trig functions, okay? Your sum of two angle formulas in trigs come out looking a lot like this. In fact, it's identically like that if you just take off the h's everywhere, here, 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 and here. Those would be the same. And then the hyperbolic sine of the difference of two arguments. These are not angles, by the way, anymore. That's another big difference. These are just numbers. Okay, that's very similar. In fact, the same. Everything is the same pattern there. But then when you do hyperbolic cosine of the sum, that gives you a sum here, not a difference, okay? Remember, because of the difference there, the thing that looked like this with trig functions came out being cosine of 2x, okay? That's not the same here, okay? And then the hyperbolic, the difference in those two would then be the opposite sign here. If you combine this, okay, okay, here we go. I would have done this one after this one. Put x equal y here, and you just wind up with exactly the same form we had for hyperbolic, for trig function sine 2x. Do the same thing for cosine, hyperbolic cosecant, but because of the plus here, you get a sum here, not a difference, okay? Now in trig functions, this would have given you 1. Now it gives you the hyperbolic cosine of 2x. Here this would have given you in trig functions a cosine of 2x. Here it gives you 1. So like I said, just similar enough to screw you up, okay? So that's why I don't really like messing with them. You have to look them up every time. I don't ever try to memorize these. Now if you take this form here and combine it with that form there, you will get the hyperbolic sine squared x, another expression for that, which is somewhat similar to what we have in trig functions, not quite the same. And you do the same thing for hyperbolic cosine. And this is almost identical to what you get with with regular trig functions. But again, so many of the things are similar, meaning almost the same, and others are so close to being the same, but with a sign difference that always is going to me screw you up. Okay. Now, how about differentiating and integrating hyperbolic functions? Okay, here are the rules. Again, if you need it. Because the hyperbolic functions are written in terms of e to the x, e to the minus x, you can easily derive these rules for derivatives. So why do it? Just use e to the x, e to the minus x, and stay with it and not make up something like this. But derivative of hyperbolic sine is hyperbolic cosine. Similar. Derivative of hyperbolic cosine is hyperbolic sine, not minus hyperbolic sine. So again, just this is the same, that's different, just by a sign. And hyperbolic derivative of hyperbolic tangent is indeed hyperbolic secant squared, okay? Cotangent minus hyperbolic cosecant squared. Derivative of secant, hyperbolic secant of u would be minus, whereas for sines, for trig functions, it's secant x tangent x. Now it's minus secant x, and this is the same. So this is opposite sign, that's the same sign. This is same sign, this is opposite sign. These two happen to come out being the same. Okay, so then when you integrate, again, you integrate cosine, hyperbolic cosine, you get hyperbolic sine, just like you do with trig. But when you integrate hyperbolic sine, you still get hyperbolic cosine, not negative, like it is with trig functions. Integrate this, you get that, just like it is with this. Integrate this, you get that, just like it is with trig. Do this one, and you get minus hyperbolic secant, not like so you get secant, and here you get, so these, again, this one, and that one are the same. This one and that one are different. That's the same. So it's enough to throw you off. Okay. Now I'm not going to do the examples unless someone really wants me to. Anyone want to see this example worked out? I didn't hear. Say again? Was that it? Yes or no? You do want to see it worked out. All right. Thank you so much for that. Okay. All right. Here's what we do. Okay. You basically go back to the table we just had. Whoops. Go back to the table we just had. No, not that one. This one. Okay. And, okay, let's look at the similarities. This is hyperbolic derivative of hyperbolic sine of x squared minus 3. Okay, actually this table is a derivative of hyperbolic sine of x squared plus 3 would be hyperbolic cosine of x squared plus 3 times 2x. It's just simply the chain rule, and that's what you get here too. Do you see that? You use the chain rule just like you do in anything else. It's just that you use derivative of hyperbolic sine is hyperbolic cosine. Okay, so that part is exactly the same, and then you do the chain rule of this part. That would be the 2x, and that's where the 2x comes from. Just like if that would have been a derivative of sine of x squared minus 3, that would be cosine of x squared minus 3 times 2x. So no difference there, because that rule is the same. Okay. All right. Your log issue will be the same. Now, is that legal to put that way? Let's go back and look at our graph. Cosine, hyperbolic cosine is always positive. So yes, it's perfectly good to not use an absolute value bar when you're dealing with our hyperbolic cosine, if you're taking the log of it. Log of a hyperbolic sine, you better use an absolute value bar. Hyperbolic tangent, you better use a hyperbolic cosecant, hyperbolic cotangent, but hyperbolic secant and cosine, you don't need the absolute value bars. Okay? So this one, would be 1 over hyperbolic cosine times the derivative of hyperbolic cosine, which is hyperbolic sine. So it's the same way. The procedures are the same. It's just you have to remember what those values are, what the derivatives of hyperbolics are. Okay, and that is, by the way, hyperbolic tangent. Okay, I don't remember if that same formula works for trig functions. It may. I'm not doing it in my head right now. Okay, how about this one? Derivative of a sum times a difference. Well, here's a product rule. Okay, the product rule still works. The derivative of this would be x times the derivative of that. That would be x times hyperbolic cosine. Okay, plus the second times the derivative of the first, which would just be hyperbolic sine, minus derivative of hyperbolic cosine is hyperbolic sine. So it works the same way. Once you know what the derivatives are from that previous table, you just use them. Okay, your other things, your other rules, the product rules, the quotient rules, the log rules, the power rules, everything else still works. It's just doing that step that takes the derivative of a hyperbolic. You have to know what they are. Now, because sine hyperbolic sine minus hyperbolic sine is still 0, this is just x times hyperbolic cosine of x. All right. This one, okay, again, a product rule, okay, but now they've thrown in, I think this is an error, okay, it better be an error. I don't think there's any way you can do that. Yeah, the D part, this is a hyperbolic sine here. That is not sine. It's hyperbolic sine. In your book, it's correct. Okay, so let's see what this is. Okay, now actually how I would do this one, I would split this into x hyperbolic cosine minus hyperbolic cosine minus hyperbolic sine. Okay, and on that first one, derivative of a product rule would be the first times derivative of the second, that'd be x hyperbolic sine. So that's right. Okay, the next one would be minus derivative, oh yeah, then the second would be hyperbolic plus hyperbolic cosine. Okay, and that's that term. Okay, then you'd have derivative of minus hyperbolic cosine would be minus hyperbolic sine. There it is here, minus hyperbolic sine. And the derivative of hyperbolic sine would be, minus hyperbolic sine would be minus hyperbolic cosine. And these two are going to add to 0, so you get, just like you did before, x minus 1. Sorry. Is that blocking your view? Now it disappeared. X minus 1 times hyperbolic sine. It's just, you have to go back and make sure you use the right derivatives, you know, the right signs on your derivatives. That's the only difference here. All the other rules apply. Okay. Inverse hyperbolic functions. Unlike trigonometric functions, hyperbolic functions are not periodic. I've already said that. You can see that 4 of the 6 hyperbolic functions are actually one-to-one. So let's go back and see that by the graphs here. This is a one-to-one function. Hyperbolic sine is one-to-one. Hyperbolic cosine is not. Okay? You would have to define it from 0 to positive infinity or negative infinity to 0. Hyperbolic cosine is not one-to-one, not over its entire range. Hyperbolic tangent is one-to-one over its entire range. Hyperbolic cosecant is one-to-one over its entire range. Of course, it's not defined at x equals 0. Okay, so you have to be on one side or the other of that. Hyperbolic secant is not one-to-one. Again, you'd either do from x to positive infinity or from 0 to positive infinity or negative infinity to 0. One or the other. This is one-to-one. Hyperbolic tangent Looks awfully close to hyperbolic cosecant, but it's not the same. They are different. They're going to different limits here, but they are one-to-one functions. So 4 of the 6 are one-to-one. Okay, so that's why they said inverse hyperbolic. You see that 4 of the 6 hyperbolic functions are actually one-to-one. Hyperbolic sine, tangents, cosecant, and cotangent. So you can conclude that those 4 functions do have inverse functions defined for all real numbers. The other 2, hyperbolic cosine and hyperbolic secant, are one-to-one when their domains are restricted to positive real. Why is this doing this? Okay, evidently I just lost Zoom, so I'm guessing you cannot hear me. This happened yesterday. I don't know if there's a storm in the area or if Zoom is just screwing up. And I think part of the problem is my internet I still got, yuck. Okay. I'm going to do something bizarre here. I'm going to close that. I'm going to change my provider here and see if I get any better. I still have no internet access. Yuck. All right, I think I just got it back. Let's see if my other one will come back. Nope, no internet connection there. So, yuck. All right. All right, I don't know what's going on here. I have internet, but now Zoom isn't it's trying to connect, but not connecting as fast as it normally does. This is so frustrating. Leave meeting and try it again. Okay, it's trying to connect again. All right, I'm going to stand for a while because I get tired of sitting. assuming y'all can't hear me, but I'll keep talking just in case anything picks up again. All right, it looks like we may be back. Okay. Okay, can anyone hear me yet? I see, okay, good. I lost internet, and so I had to change providers, and I did, but it took forever for the second one to connect. So I don't know how many we still have. Well, we still have 13 people here, so we didn't lose too many. 12 people here dropped as we're talking. So let's go back to share the screen, and we were on inverse hyperbolic functions, and let me move this down out of the way here. And I'm trying to remember, is this the slide that we were on? Okay. Yeah, I think this is where we were. We're just talking about the other two, hyperbolic cosine and hyperbolic secant, are one-to-one when their domains are restricted to positive real numbers or negative real numbers. They just say positive here. For this restricted domain, they also have inverse functions. Okay. Now it won't advance. No, okay. Because the hyperbolic functions are defined in terms of exponential functions, it's not surprising to find that the inverse hyperbolic functions can be written in terms of logarithmic functions. And here is the theorem. The inverse hyperbolic sine is merely a log function. Its domain, all real numbers. Okay? Because nothing's going to bother here because that's always positive, and if that's always positive, square root of x squared plus 1 is always greater than x, even when x is negative, because you square it and add 1 to it and take a square root of it, it's going to be something greater than x. So this is always positive. Inverse hyperbolic cosine is very similar, okay, except you have a minus here. But here you have to restrict the domain to 1 to positive infinity. Not 0 to positive infinity. That won't work, because that would be 0 would give you a negative in the yuck. I did that. Sorry about that. In a square root, and you can't do that. So you have to be outside of 1, from 1 on up. And since you're only in positive values here, that works here too. Inverse tangent will be 1/2 the log of the quotient of these two. Now, the domain here for this definition of this is from -1 to 1. Now, obviously a 1 won't work because you'd have that in the denominator, and anything beyond -1 wouldn't work because then your denominator would be negative. Okay, no, I'm sorry, greater than 1 wouldn't work because your denominator would be negative, numerator would be positive. That would be a negative fraction. You can't take the log of a negative number. But if you're less than -1, then this would be negative, that would be positive, and you still can't take the log of a negative number. So inverse hyperbolic tangent, this definition of it only is good from -1 to 1. Whereas inverse hyperbolic cotangent, the other is true because you reverse the order of these two. reverse them down here, and now you can't have anything in between -1 and 1. Here the only place it's defined is between -1 and 1. Here the only place it's not defined is between -1 and 1. And -1 and 1 don't work in either place. Okay. Inverse hyperbolic cosecant. It's kind of messy, but there it is. And that's only good from 0 to 1. This definition is only good from 0 to 1. Not counting 0, because you can't have 0 in the denominator. You can have 1 here, because 1 minus 1 is 0, and you can take the log of 1. So that would be okay. Okay. But you can't have anything beyond that. This goes negative. You can't do that. Inverse hyperbolic cosecant. Again, you can't have 0 because of that and that. Okay. And basically anything negative or anything positive, but it can't be 0. That's the only thing that's disallowed. This is always positive, so where's my cursor? Come on back. There it is. This is always positive, so that allows for that. Even when x is negative, this is always positive. Okay. The graphs of these inverse hyperbolic functions are shown here, just as you would expect, since the hyperbolic sign went something like this. Inverse hyperbolic sign goes something like that. Hyperbolic cosine started here and went positive like this. This would be reflected across the identity function, and it goes like that. Remember, hyperbolic tangent looked a lot like an inverse tangent function, so this, just flip it over, and there it is. But it's only limited from -1 to 1. Okay? Inverse hyperbolic cosecant basically looks just like it. I mean, take a look at that. This one right here. Take a look at this one and compare that to that one. They look almost identical. Okay? They're probably not exactly identical, but sure look similar. Remember your hyperbolic sign, whereas this is curving downward, it curves upward here. This in here is almost the same, and then it curves down here. Not downward, but the second derivative is decreasing. Here the second derivative is increasing. Here, take this and reflect it over here, and that goes like this. Okay? Take this one, because its range is between -1 and 1. When you do the inverse, the domain's between -1 and 1. And then this just flips somehow. Okay, let's go back to the hyperbolics. You expect the other to look something like this, only the dotted lines are going to be vertical, not horizontal. And this will then be something that looks like this. Yeah, so anyway. All right. Like I said, this looks the same. This was something, remember, the hyperbolic secant came here and went like this. This one comes here and goes like that. Okay. And this, like I said, before these were horizontal asymptotes, now they're vertical asymptotes. But other than that, they look the same. Okay. Now, attractics. Okay. A person holding a rope that is tied to a boat, as shown here. As the person walks along the dock, looks like he's going to fall off in a little while, but let's not do that. The boat travels along a traxis. If the boat was out here to begin with, and the person was here, and now it pulls here, it's pulling the boat along what they call a traxis. That's the track. Okay? And here is the equation that gives you that traxis. Okay? Where A is the length of the rope, X is your variable. How far from the dock the boat is, basically. For A is equal to 20 feet, and that's where it started. When the person started here, boat was out here, and then as he walks along, the boat slowly gets a little closer, and if the dock was long enough, it would come alongside eventually. In reality, no, but an actual boat has width to it, so it would. For A equals 20 feet, find the distance the person must walk to bring the boat to a position 5 feet from the dock. Okay? Well, the Y is the distance the person must walk. Okay? The X is how far the boat is from the dock. So you plug in a 5 here and a 5 here with a 20 there, there, and there, and you see how far the person must walk. Okay, and notice that the distance the person walks is Y1, which is where they've done some magic here, haven't they? Okay, it says from the, oh, okay, I see what they're saying. All right, the boat is moved from 20 away to 5 away. So the amount the boat is moving is your X, and that's what we're talking about here. Okay, how far the person has walked, since this is always 20, okay, how far the person has walked is the square root of 20 squared minus X squared, okay, which is exactly what you see here. Okay, that's beside the point. Okay, so the distance the person has walked is that. This is how far, this is the variable Y. This, oh wait, here's somebody. I think this may be Esther coming back. I've already got her here. Okay. Okay, Esther, if you're back in, sorry about that. Obviously we lost internet here. I don't know why. Like I said, there are some rain showers in the area. I don't think that should affect internet pickup, but we're down in a hole is where we live. 3 streets that come into us are all downhill in all 3 directions, with a slight downhill leaving from where we are, moving to the north. So down in here with all the big trees around and stuff like this, I guess if conditions aren't perfect, we'll lose internet, and evidently that's what happened. So I'm glad you made it back. We're doing example 5 in 5.9, which we're not responsible for, and this, by the way, is on page 378. And this is the distance the person has walked according to this. Well, now it won't advance. Okay, according here, the distance the person walked to here, Y1, okay, from Y is equal to 0 to down here. You can't really see it because that box is in the way, but here's Y is equal to 0 to here. That's your Y1, whereas Y is the variable how far you've walked, and this triangle here says the Y1 oh, I'm sorry. Y is the position of the boat. I'm sorry, not the position of the person. The position of the boat is the XY. So as the boat is moving from here to wherever it's moving to, this is your Y here. So the Y then is I would say it the other way. Y is that expression for X minus or Y1 minus that expression for X. Okay. So anyway, there's your Y. The Y is the difference between Y1 and this value here. That's what this Y is. And the So this is a really convoluted type of problem, and that's because traxuses are hard to calculate. And this, if you look at that, now that I see the y is the coordinate for the boat, the y1 where the person is that y, that's the thing, plus minus this thing right here. Okay, right, did I say that right? No, it's the y plus this thing right here. So that's why, where they get this formula here. Okay, now the y is that right here, a inverse hyperbolic secant blah 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 that way. Okay, and that's what you put in here, and then you add this part. Well, this part and that part are identically the same, so they disappear. So your y1 is simply 20 hyperbolic secant of x over 20. Okay, now, and then all you do is plug in when x is equal to 5, plug that in here, and you have the y1 is, and then what they do is plug in that formula we use for hyperbolic secant, which was back here. One more. Inverse hyperbolic secant is this expression right here, log of 1 plus blah 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 1 minus x squared. And so this is what you plug in for inverse hyperbolic secant. Okay, and you can't see it because this box is in the way. It'll fade out in a minute, I hope. Here it goes. I don't know why they put this crazy box in here. It just gets in the way of what you're doing. So anyway, you plug in that formula, the log function for that, plug in the numbers, and you get about 41.27 feet. So if that's something you think you'll be needing to do in the future, by all means, get familiar with these hyperbolic functions. So the person must walk about 41.27 feet, I'd say 41.25 feet, to bring the boat to a position 5 feet from the dock. Okay. Now, what if we're differentiating and integrating these hyperbolic functions? I don't even want to think about it. The derivatives of inverse hyperbolic functions, which resemble the derivatives of inverse trigonometric functions, only different. The theorem on the next slide are listed on the theorem with the next slide with the corresponding integration formulas in log form. You can verify each of those by applying log different definitions to inverse hyperbolic functions. All right, so if you're taking the derivative of a hyperbolic sine, it looks fairly similar to that of a derivative of a sine, except down here sine would be 1 minus u squared, not 1 plus. Okay, cosine would be 1 minus u squared too. Now it's u squared minus 1. Okay, hyperbolic tangent in sine, in tangent, not hyperbolic tangent, that would be a plus down here. And hyperbolic cotangent, if you did do the inverse cotangent function, I think it's probably not this similar, okay, but anyway, because I don't even use inverse cotangents very frequently. It's just something that's not very useful or well done. But anyway, here they are. Now, then when you reverse this and do your integrations, if you're integrating u squared plus or minus a squared, that plus the square root, that would be this or that, you get the log of this thing, and your plus or minus goes in here. Okay? When you're doing the difference, that would be tangent cotangent, hyperbolic tangent cotangent, then that's what you would get. But then when you plug in what the log functions are, that's what you get here. Okay, and then this again looks a lot like you would have for secant, tangent, or trig secant or cosecant. It would be something that looks similar to this. Your plus or minus A would be plus or minus A up here. All right. Again, I would never memorize these. If I ever needed them, I'd look them up in a table, okay, and go with them. Because frankly, especially down here, you don't even have to mention that they're hyperbolics. You go straight from this form to a log form. That's all. So why mess with hyperbolics? Go straight to the log. Yeah. Anyway, whoops, I hit the wrong key. Sorry about that. Okay. Now this is just asking you to do the very thing that we said before. Use the formula. Derivative of inverse hyperbolic sine of 2x. I'll tell you what, the chain rule is going to give you the 2 up here. And the derivative of this would then be simply what we had here. Derivative of that would be u prime, which was our 2, over the square root of u squared plus 1. And your u was 2x squared, 2x in parentheses squared plus 1, the square root of that, and that would be 2 over the square root of 4x squared plus 1. Yeah. Okay. Derivative of hyperbolic tangent of that would be derivative of the du, which is, here's your u, 3x squared, that's up here, and then remember, whereas a tangent would be a plus here, hyperbolic tangent, inverse hyperbolic tangent would be a minus here. So it's the 1 minus this argument squared, which would be 3x squared over 1 minus x to the 6th. And there it is. And that's the end of section 5.9. I'm not going to make any homework assignments here. If you feel like you need to be familiar with these, you pick out the ones that seem closest to whatever your field of study is and go for them. All the odds are at calcchat.com. The ones that are in red, if you do have this book, those are at calcview.com. Now, if you feel like you need more practice on chapter 5, there's review exercises here. Now, there aren't any at CalcView, they're all at CalcChat, and again, it's odd numbers, so either any of the odds 1 through 5, 7 or 9, 11, 13, 15, 17 or 19, 21 or 21, 23 or 25, 27, 29, 31, 33, 35 to 39, 41 or 43, 45, 47, either 49 or 51, any of the odds 53 to 61, 63 to 69, 71 to 77, 79 to 80 or 81, 79 to 83, 85 or 87, 89 to 93, 95 or 97, and 99 or 101. There is another problem-solving thing at here, and you can go to CalcChat and walk your way through the odd number questions there too. All right. Now, let's talk about the test. I hope everybody's here is back who was here before, but we may have lost some people. But if they pick up the Screencast-O-Matic, the thing, And silly me, I forgot to turn that off when we didn't have class and when the internet went out. So you'll hear me fussing at the system, that's there. So sorry about that. I should have turned off the recording. But here's what. I put the test for Chapter 5, only covering 5.1 through 5.8. I put it out there under Blackboard Messages. Now I put it out there in Word format because that's what I thought most people could read. And then at least one student has indicated to me she couldn't read the integrals. Okay, and sure enough, she showed me. She sent a picture of what her printout showed, and it left off every integral. And the only thing I can figure with that is this: that her version of Word must not be the same as my version of Word. And I said this in the email I sent to her, and it absolutely an aggravating truth about Microsoft. Microsoft loves to update versions and not make them compatible with earlier versions. And that's exactly what happened here. In my mind, I don't know what happened, but that's the only thing I can figure out. They came out with a new version, and because they're trying to sell more product, they make them incompatible with the older versions. Okay. Now, if I were still using WordPerfect, if y'all could read those, that would have been an easy thing to do. They haven't changed their equation editor in years, and it's still so much better than anything Microsoft has ever come out with. But no one uses WordPerfect, so can't do that. So what I did, I printed the very thing that I put on the file that she couldn't read, printed it off of Blackboard, which mine had all the integrals in there, and then I took a picture of it and sent it as a PDF file. So that's also there. You'll see two tests too. One is Word docx or whatever they call that, and the other is PDF. You can print off, if your Word version will read that Word version, you can use that. If it won't, and if you prefer PDF, will work no matter what. Okay, so that's there. And somebody was asking earlier, before everybody was in class, when is it due? Technically, a week from today. But if you need more time, take it. Just be sure you get it back to me before I give you the next test, which is going to be a ways off. Now, the next chapter is Chapter 6, which is differential equations. Here at Lawson, I think at most schools, that's a separate course. So I'm not going to do differential equations here. We're going to skip Chapter 6. Okay? You'll pick up differential equations when you finish Cal 3. Okay? So we're moving to Chapter 7. And it's a very logical kind of move. Okay, screen sharing stopped. I'm going to have to let me get rid of that file and start back with Chapter 7. There it is. Nope, that's not it. This aggravates me about Zoom. They blacken out what's here. I'm going to try this and see if this works. Yeah, this is it. This is it right here. Okay, there we go. Here's Chapter 7, and we'll start from current slide. Chapter 7 is applications of integration, which to me makes perfect sense to follow Chapter 5 with, rather than having differential equations thrown in between. So, moving on to Chapter 7. 7.1 is talking about the area of a region between two curves. Now, we came really close to doing that. We did area of a region over the x-axis. Well, now we're just going, I'm sorry, I hit the wrong key here. I'm just moving this out of the way. Okay. Now we're going to deal with area of a region between two curves. Okay, not just above the x-axis. X-axis is a curve, so we were sort of doing this before, but this time we're going to have the other. So for some reason it won't advance. I have to click on the screen to get it to advance. There we go. Here are our objectives in 7.1. Okay. By the way, there are 7 sections in this chapter, and unfortunately we probably need to do just about all of them. We may skip a little bit in 7.6, but we'll try to move along in chapter 7. Okay. And by the way, this is applications. The next chapter we do is techniques of integration, which actually to me it almost would have made more sense to do techniques before applications, but they chose, as a lot of books do, to put applications next. So find the area of a region between two curves using integration. It's going to be pretty straightforward from what we already know. Find the area of a region between intersecting curves using integration, which is just a slight difference, and describe integration as a accumulation process. I think we've already sort of done that before. We'll do it again here. With a few modifications, you can extend the application of definite integrals from an area of a region under a curve to the area of a region between two curves. Let's consider two functions, f and g. Both are continuous on some interval a to b. So they're continuous from a to b. Here's your f going up like this, and here's your g going like this. Now, in between x equal a and x equal b, f is always greater than g in that region. If you went out here, no, it's reversed. If you went over here, no, it would be reversed. But anywhere between a and b, and even if you went to here to there, they would be, f would be greater than g. That's a requirement here. The graph of f on the interval you're dealing with has to be f and g both lie above the x-axis. That's not necessary. And the graph of g lies below the graph of f. That's what I'm just saying. We're going to start with both of these being positive on the interval. Obviously, f goes negative, it looks like somewhere down here, and probably over here too. We're not going there. We're only going to stay where both f and g are positive, above the x-axis, and f is always greater than g. So anywhere in between that intersection and this intersection, we've got it knocked. A and b are within those. So what's the area of the region between the two curves? Well, it doesn't take a lot of imagination, I don't think, to say, well, what's the area of f between those two curves? Well, that would be everywhere inside these dotted lines, right? And beneath f. Well, what's the area under g between those two values? Well, that would be the white part between these dotted red lines. If you subtract what f is from g, this is what's left. So there's the region, the area of the region between those two curves. Okay? You can geometrically interpret the area of the region between the graphs, and this is the same thing I did, as the graph of f subtracted from the area under the region of f. G subtracted from that of f. And this is saying what I just did. This is the area, the pink in here is the area under f between a and b above the x-axis. This pink here is the area under g between a and b at the x-axis. And if you subtract this off of here, you're left with the area here. So the area of the region between f and g is the integral from a to b. X is going from a to b. Dx indicates that x is what you talk about here, of f of x minus g of x. The other way you could think of this, draw your little rectangles. Delta x is here, and you're doing the little rectangle that the height here is f minus g. The width is delta x. That's what you got. F minus g times delta x dx. Summation of that. Okay. Should be nothing super surprising or new there. Follows from what we've already done. To verify the reasonableness of the result, and this is what I was just saying, you can partition it into n subintervals, each of width delta x, just like I was saying. Then as shown in this figure, the sketch of a representative rectangle would be f here minus gf here. That would be the length of that rectangle. Width is delta x. So your area would be f of x minus g of x times delta x. Do that, sum that over the whole interval from a to b, and let the delta x go to 0, and you've got an integral. Okay. So again, nothing too new here. The area of that representative rectangle is the length, the height is f minus g, the width is delta x. By adding those areas of the n rectangles, then take the limit as the norm, that's what that's called, the norm, that's the length of the largest one of those widths there, approaches 0. That means all the smaller ones have to be at 0. In other words, n is going to infinity. You go from this limit here of a summation from I is equal to 1 to n of the difference between those times delta x, and the summation becomes an integral, and the integral is the difference between those two functions, and then the delta x goes to dx. Okay, that would be the area. Because f and g are both continuous, f minus g is continuous, the limit exists, so the area is given by that. Any questions? A lot of blah, 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 blah. So here again, they're going to say the same thing again. If f and g are both continuous functions on some interval a to b, and you're guaranteed on that interval that g of x is always either less than or equal to f for every x in that a to b, okay, then the area of the region bounded by the graphs of f and g, and the vertical lines x equal a to x equal b, is just that area, the integral from a to b, f of x minus g of x dx. Seems like it's pretty clear cut, okay, and they spent slide after slide describing it. Okay, and here we go again. In figure 7.1, the graphs of f and g are shown above the x-axis. However, as I indicated, that is not necessary, because the difference between these two, if you took this whole entity here and dropped it down till it was here, and the f was up here and the g was down here, the area is the same. If you just did a vertical translation and drop it down, they both don't have to be above the x-axis. Neither one of them has to be above the x-axis. You're still doing the difference of the upper one minus the lower one times your dx. And that's going to be true whether they're both positive, one's positive, one negative. It doesn't matter. That's still the same integral. F minus g can be used as long as f and g are continuous, and g of x is always less than or equal to f of x for every x on the interval a to b. So that requirement, they both be above the x-axis, no longer a requirement. Certainly it's true if it's there, so nothing's wrong with saying it, but it's not a requirement. And this is graphically what I was just saying. You drop that same shape that we had there from up there to down here, the area is the same. The difference is the same. The f minus g is the same. The dx's are the same. Everything's the same. It's just that one of them's below. They can both be below the x-axis. This one's still greater than that one, so the difference between f and g is always positive. That's the important part. And the delta x is the same. Nothing changed, whether you're up there, down here, or even below the x-axis. Okay? Enough of that? All right. Representative rectangles are used throughout this chapter in various applications of integration. A vertical rectangle of width delta x implies the integration with respect to x, whereas a horizontal rectangle of width delta y, that represents integration with respect to y. Okay. So here's example 1. Find the area. Whoa, here's somebody. I can't see the name. Can anyone see that? Let me see if when I admit. Houston's here. Good deal. Okay. Houston, I don't know if you were trying to get here earlier. We did have a, I'm guessing about 5 to 10 minute break in the middle of class where my internet went out. So there wasn't anything. If you tried to get in at that time, you weren't able to, but hopefully that wasn't the case, but I'm glad you're here now. Okay, we finished chapter 5. The test for chapter 5 is out there on Blackboard under messages. It's there are actually two versions of the test there. One is a Word version, one's a PDF version. Same test, it's just that some people indicated they could not read the Word version because that left off all the integrals. That's what the whole test was about. So I took a picture of this very same thing that was there in Word version and took it in PDF, and everybody should be able to do that one. So use whichever one. You don't have to do it but once, but use whichever version you want. And when you finish it, send it back to me either as a PDF. If you kept it as a Word and want to type in your answers, you can do that. If you want to take a picture of it and send it, you can either send it through Messenger, Blackboard messages, or you can send it through regular email. Either one will work. All right, so we finished chapter 5. We're in chapter 7. We're right now on bottom of page 445 in chapter 7. Find the area of a region bounded by the graphs of y is equal to x squared plus 2 and y is equal to minus x, and the line x equals 0 and x equal 1. Now, here's how I would start this problem. I would start and let this endpoint, x equals 0, plug it in here. There your y is equal to 2, here's your y is equal to 0. That indicates to me this y is greater than this y. But let's do it at the other end. Plug in a 1 there. 1 squared plus 2 would be 3. This would be a negative 1. That's even further apart. So I think this whole thing, the y squared plus 2, is always greater than or equal to minus x. Okay? That's pretty obvious from looking at it, but you just sort of verified it. So what we're going to do, and I'm going to go to a white page, whiteboard, and we'll go here, and of course now my taskbar again is in the way. So let me move that as far out of the way as I can. If y'all do watch the YouTube video of this, you'll see what I'm talking about, because that will show up on that. It doesn't show up on your screen now, but it'll show up on my screen because that's what this is capturing. All right, so let's write again. Find the area of the region bounded by the graphs of y is equal to x squared plus 1 y is equal to minus x basically, let me get it all written first. X equals 0 and x equal 1. Wonder if this is painful for you to watch me write as it is for me to write. But in other words, any x is positive, which is all these are between 0 and 1, x squared plus 1 is always positive and minus x is always negative. So obviously this one's on top. So it says find the area of that region. That's an integral of the first one, x squared plus 1 minus the second one. Well, minus a minus x would be a plus x. And then you do your dx, the increment, and you're doing the dx's from 0 to 1. Now on your test, I was sort of surprised that the integral signs, the integral, when I did a definite integral, that really did look pretty much like what I was putting in. However, when I did do the limit on that test, I put I can't remember what it was, let's just say I equal 1 to 17 or whatever n or whatever it was on top. I wrote them in that way, but then when they did them, Word did the translation of them, it put the limits off to the side. So when it says the limit and the things are off to the side, that would have been top and bottom. Word just wouldn't do top and bottom. I don't know why. It did the integrals okay, but it didn't do the limits okay. So hopefully that will make sense to you. If you need me to review that or go over it, I'll be glad to. All right. Guess what? That was the hard part of the problem. The calculus part is the easy part. What's the antiderivative of x squared? Someone tell me. Anybody? X cubed over 3. You increase the exponent by 1 and divide by that new exponent. Plus, how about 1? What's the antiderivative of 1? Anybody? X. Perfect. Okay. And what's the antiderivative of x? Again, x squared over 2. Perfect. Okay. And we evaluate that from 0 to 1. Okay. I'll do the 1 part first. Or you could do it too. That'd just be 1/3 plus 1 plus 1/2. Everybody see what I'm doing? That's plugging the 1 in and plugging the 0 in and subtract. That'll be -0, -0, -0. Okay, so this is your answer. That looks like to me to be 1 is 6/6, 1/3 is 2/6, and 1/2 is 3/6. So 6 and 2 and 3 would be 11/6, I believe. I'm doing it quickly in my head, or not that quickly, but I believe that answer is 11/6. Actually, easier to me would be 1 and 5/6, which is 11/6. Except I got it wrong. If I had written the problem down right, it would have been correct. Okay, this was x squared plus 2. I'm sorry. I don't know where the eyes or the brain was at the time, but this is a 2, and nobody corrected me. Not a single soul. Okay. Okay. So let's go back and do it right. This is x squared plus 2. That puts the 2 in here. All that talking I did about it, you did. So this would then be a 2x here, and this would be 1/3 plus 2. 2 times 1 is 2, plus 1/2, and that would then be 12/6 plus 5/6 would be 17/6. Okay. There, it's right. Look, folks, when you see me making a mistake, catch me. Let's not have to go back and recreate the wheel. All right. Any questions on that? Once you get the problem right, you should get the answer right. Any questions? Now, I'm going to clear the drawing. Well, let's see. I think what we'll do is go back to another screen share. Oh, let's watch how they did it. Why not? Okay, this is where the PowerPoints were. We'll go from whatever the current slide was there. Okay, there's your problem, and there, sure enough, is an x squared plus 2. I don't know why it became a 1, but it did. And g of x is going to be the lower one, and f of x is the upper one. You don't have to draw the picture, but this picture certainly makes it more graphic, more obvious. This one is starting from up here rather than the one I did was down here, so that's why we had a smaller value. The F is always on top, the G is always on bottom, so it's F minus G. G is always less than or equal F on all the X's in between 0 and 1. In fact, I would contend it's always going to be that way because this is only going up linearly here and this is going up in a quadratic sense, so that's going to always beat the other one. So this would be good for any interval you chose to write on, okay? Not just 0 to 1. But we chose 0 to 1, or the book did. Okay, so the area, and you can go through all this if you want to, is the length of that rectangle, F minus G, times the width of the rectangle, delta X. And that would be X squared plus 2, not 1, minus a minus X times dx. And that would be, give you this area, be the integral from B to A to B, from 0 to 1, of x squared plus 2 minus a minus x, which is plus x. Why? They do all that at the top and then go back and reinvent the wheel down here. Yep, there you have it, 0 to 1 of x squared minus 2 minus a minus x, which is plus x, dx. And that would be, now they changed the order, it didn't matter. That's x cubed over 3, the x squared over 2 from this one with a plus sign because minus and minus is plus, and then plus 2 would be plus 2x. Evaluate from 1 to 0 to 1 and you'd have 1/3 plus 1/2 plus 2, which is 7/2, which we got once we put the 2 in there. Any questions on that? All right. The next thing, this is on page 446, and let's see, we go until 2:30, right? No, 2:25. So we just got just less than an hour to go. I know I didn't take advantage of the break when I had it because I didn't want y'all coming back and I wasn't here to receive you. So let's take a quick break right now. I call it a bladder break because it would be more comfortable to do so for me. So if you will, let's pause for a moment here. Now I'm going to turn off the sound from this microphone so you won't hear me walk out or walk back, but my wife said I could do this. I think this is how. Yes, okay, thank you. All right, so now we're going to hit area of a region between two intersecting curves. Now the only new thing that this is bringing to the table is finding the points of intersection. Okay, before they told us what those limits were between here and here, and we checked to make sure that alpha is still greater than g and that kind of stuff. So if you got two intersecting curves, if you're in between the 2 points of intersection, you know one function is going to be greater than the other as long as they don't intersect multiple times in there. Okay, so that's what we're going to be doing differently here if I can get the screen to advance. There we go. In example 1, the graphs of f of x is x squared plus 2 and g of x minus x never intersected. So the values a and b were given explicitly. A more common problem, though, involves the area of a region bounded by 2 intersecting graphs where the values of a and b must be calculated. And that's the difference in what we're doing now. So here's example 2. Find the area of the region bounded by the graphs of f of x is 2 minus x squared and g of x is equal to x. Okay, now just glancing at this, I would say g is always going to be greater than f. Okay, no, it won't always be. Okay, so what we got to figure out is the point of intersection. Well, what are the points of intersection? That's where f is equal to g. So let's go back to the whiteboard, painful as it is, and clear my drawings. and I guess we're pretty much okay what we have now. Okay, so let's repeat the problem here. Find the area of the region bounded by the graphs of f of x is 2 minus x squared, okay? G of x is x, okay. So that's the problem. Find the area of the region bounded by those two graphs. So in other words, these two graphs are somehow going to enclose an area. So the first thing we do is find out where they're equal. Okay, so we set that down. We say, where is 2 minus x squared equal to x? Okay, now that's going to be a quadratic equation. And because I usually like quadratic equations to start with positives for the quadratic term, I'm going to move this term over here, and that'll move this term over here. So that's going to be x squared plus x, because that was already over there, minus 2. Okay, and now that's equal to 0 because I moved all those from the what was my left hand side. I moved them to the right, but then flipped sides and moved them back. So now the right hand side, which was the left hand side, is now 0, if that made any sense. Okay, how do we solve this? That's good old algebra. Factor. Only possible factorization for x squared, of course, is x times x. And then, because the sign of the last term is negative, you know one of these is going to be positive and one's going to be negative. Only way you can get a negative product out of two signs, okay? Now, who's going to wind up winning? The positive sign. So that's going to be the larger number. What's the only possible factorization of 2? 2 and 1. Now, there's no guarantee this is going to be the answer, but let's at least check it and see. X times x is x squared. That's foiling it. Okay. X times minus 1 is minus x plus 2x. That's going to be plus x minus 2. Sure enough, that works. Okay. What does that give us? That means those two are equal either when x is equal to negative 2. Now I'm skipping some steps because I don't like to write on the screen. Or when x is equal to 1. Am I losing anybody by doing that? I hope not, but if I am, I'll go in and put in the intermediate steps. Was that okay to do it that way? The intermediate step, of course, is set each of these equal to 0 because of the zero product principle. If the product of these two is equal to 0, either x plus 2 is equal to 0, which yields x equal minus 2, or x minus 1 is equal to 0, which yields x equal 1. If you do the math, you'll see that. So we're going from minus 2 to 1. Well, let's pick a value in between minus 2 and 1. How about 0? That's one of my favorite numbers in the world. At 0, this is 2 and that's 0. So f of x looks like it's always on top between minus 2 and 1. Now, you can look at the figure in the book, which we'll be looking at in a few minutes. You see that is the case. So therefore, to do what they ask us to do is find the area of the region bounded by that. That will then be the integral from minus 2 to 1, you always do lower to higher, of the difference between these two, and that will be 2 minus x squared minus x, because it's the difference between those two. and that would be times dx. Now, you could arrange them in different order if you wanted to. There's nothing to prevent you just going and do the integration. What's the antiderivative of 2? Anybody? (2x). What's the antiderivative of x squared? Anybody?
2x.
Okay, I got the 2x. How about x squared? What's the antiderivative of that? X cubed over 3. And what's the antiderivative of x? With a minus sign in front of it is x squared over 2. The same things we did before, only in a different order, okay? That's all, okay? Now, we're going to evaluate that, because this is a definite integral, from -2 to 1. Okay, now, in this problem, remember the ones are done first, and then you subtract when you put a -2 in. Watch those signs. They're only there to trip you up. Don't let them do it. So let's put a 1 in there first. 2 times 1 is 2, minus 1 cubed is 1 over 3, would be a 1/3, minus 1 squared is 1 over 2, would be 1/2. Okay, now here's where the signs come into play, and be careful with these. You're doing a minus. In fact, it's usually a good idea to put a minus and do all your evaluation in parentheses and then go back and do it. That's a lot of writing for me, so I'm going to skip that part, but I suggest y'all do that part, okay? Especially if it helps you from making a mistake. I promise you, I tend to make mistakes doing shortcuts, but I just don't want to write any more than I have to. So we're going to have a minus 2 times a -2, that would be a -4. Well, minus a -4 is going to be a +4, right? Okay. Then you have the minus, because you're using the -2, you're using the lower bound, minus a minus, that would give you a plus, but then when you put a -2 up here, that would be a -8, so that turns up being a -8/3. Now that's a lot of minusing going on there, and hopefully you followed it all. The first minus is because you're using the lower limit. The second minus is the one that was here. That got you to a plus. The third minus, though, was when you cubed a -2, you got a -8, so that would change it back to being a minus. Okay? Now, we still have a minus because you're using a lower limit, but you're subtracting this from it, so minus a minus is a plus, but then when you square a -2, that gives you a +4, and +4 over 2 is another 2. All right, so that appears to be our answer, as long as I didn't mess up a sign somewhere. I'm going to first deal with the thirds here. Minus 1/3 minus 8/3 would be minus 9/3. That's -3. Okay? And -3 plus 4 would be a +1. Plus 4 more would be 1 plus 4 is 5. But then you got a -1/2. So basically, to me, that is 4.5. Now, they don't usually write answers in mixed form like that, so my guess is they're going to write their answer as 9/2. And I'm hoping they got it right. Okay? Now, the other way to do this was to get everything to 6. That would be 12/6 minus 2/6. That would be 10/6 minus 3/6 would be 7/6 plus 24/6 would be 31/6 minus 16/6 would be 5/6 plus another 4/6 would be 9. I mean, whatever. You could do it that way. It should come out 9/2, and that's what it does. So again, too much messing around will get you too many problems. All right, that's how we did it. Any questions on this? Let me show you the way the book did it. You probably will like that a little bit better because they don't skip as many steps. But let's go back to the screen share of the book. And we'll go from whatever the current slide was before. There it is. Okay, so let's see what they do first. Find the area bounded by that. So they drew the graph. Thank you very much. I didn't want to draw that, so I'm glad they did. My drawing would have been pathetic. So it's going from -2 down here, x equal -2, all the way over to x equal 1 here. Now in the drawing, that's what it looks like. I would not depend on the drawing, okay, because my graphs are never very precise, okay. I would depend on algebra because algebra to me is very precise. So notice that the two graphs have 2 points of intersection. Of course, that would be the case. One's a straight line, the other's a parabola. They either go intersect once, twice, or never, okay. So this has a 2-point intersection. We're looking at the graph in between those 2 points, the area between. So to find the x-coordinates of these points, set f and g equal to each other and solve for x. So here was the f of x is 2 minus x squared, the g of x was x. Set those equal to each other, and that they led off with the minus here. Minus x squared minus x plus 2 is equal to 0. That's one general form. I prefer x squared plus x minus 2. They've just put the minus out front. That's okay too. It seems like going around your ear to spite your face here because they negated that. And this gives you -1 is never 0. This would give you x equal -2. This would give you x equal +1. Same answers we got, -2 and +1. So there are 2 points of intersection. Now, so the a here is -2, the b is +1. Because of their graph that they did, they showed that g is always less than or equal to f on that interval from -2 to +1. So therefore we do the delta a, and if you want to go through and do this, you certainly can, would be the height of that area, that rectangle would be f minus g, and the width of it is delta x, okay? And that's saying the same thing, 2 minus x squared minus x, because g of x was x, times delta x. So when you do that, take the limit all like that, the area then would be the integral from -2 to 1 of 2 minus x squared minus x dx. Now, I don't know why they kept the parentheses in there that long. It's not necessary, but they go on and do the integration and they move it around. The antiderivative of 2 is 2x. It's down here. Minus x squared would be minus x cubed over 3, and minus x would be minus x squared over 2, evaluated from -2 to 1. Plugging in those values, they don't show any of the work. Talk about skipping steps. They just wrote the answer down. So even mine showed more steps than that. So that's the same answer we got. Good for them. Any questions? Excuse me just a second. I feel like my my voice is sort of going on me, so A little carbonation helps. All right, any questions on example 2? All right, they're skipping example 3, 4, 5 before they go to this. So let's back up and do example 3, 4, and 5. Let's see. We can get some of those done anyway. Let's see. These will be strictly on the whiteboard. That's not what I wanted. Good picture, but not what I wanted. Now screen share changed. Whiteboard. Now I've got to move my toolbars out of the way because it did that weird thing there. Okay, get that out of the way and get this toolbar out of the way as much as possible anyway. Okay, so let's clear the screen. Anyone need that any longer? That was the previous problem. Let's do example 3. Bottom part of page 446. A region lying between two intersecting graphs. The sine and the cosine curves intersect infinitely many times. Bounding regions of equal area. Every time they intersect, every one of those, because they're periodic functions, and every one of those bounded regions are going to be the same. So we just pick one of them, okay? The figure 7-7, now I'm guessing some of you do not have this book. Is that right? Are you using your book from your home campus, or do some of you not have this textbook?
Yes, I don't have it.
Okay, and that was an instance. Okay, here's what the graph looks like. All right, can you see that? The sine curve is the one on top, and in that interval they got here, the cosine curve is the one on bottom in the interval they show. But you see the next one is going to be the same area as that, and the same area they're going to be repeating. So let's just use the region they show there. The region, one of those sectors that is bounded by those two graphs. Okay? So the sine and cosine curves intersect infinitely many times, bounded by equal areas. Okay? Shown in that figure I just showed you. Find the area of one of those regions. Okay? Now, let's look at, first thing we're going to do, your two functions are sine x and cosine x, so what we're going to do is set them equal to each other and find out where they intersect. So sine x equal cosine x, finding the two places where they intersect. Now that is not a particularly easy thing to do algebraically. It's not bad, but it's not all that hard. I mean, it's not a really simple thing. Okay, but if you just think about your sines and your cosines, okay, sine starts at 0, I'm doing the unit circle here, and goes up to pi halves. Cosine starts at 1 at pi halves and goes down to 0 at 0. Okay? Now where do you think they might intersect? At pi quarters. Okay? So that's going to be one point of intersection. Okay? Continue that concept around. Sine is going to continue going up while cosine is going down. Okay? And it's going to be back in the opposite sector before they cross again. Okay? And that's going to be at 5 quarters pi. Now that's one way to do this, is to do it just thinking about what you already know about sines and cosines. Okay? Now, here's how the book did it, which is another good way to do it. This just has a little bit of a problem with it, but we can overcome that, I think. Okay. What they do is divide both sides by cosine x. Okay. Divide this by cosine x. And divide this by cosine x. Okay. Now, what they get here is tangent x is equal to 1. Now, here's a point. All we're interested in is points of intersection. We're not interested in everything else, okay? And I'll explain what I mean by that in a minute, okay? So where is tangent x equal to 1? Well, obviously one answer is x equal pi quarters. We know tangent x there is 1, and that's one of the points we got to before, pi quarters. Okay. Now, if you picture the tangent x curve, it starts at negative infinity near negative pi halves, goes up to 0 at 0, and then crosses at 1 at pi quarters, and then goes to positive infinity. Well, where's the next time that's going to happen? Well, it went to positive infinity at positive pi halves, and that's where it picks up again. The y value would be down there near negative infinity, coming up, crossing the x-axis again at pi, and then it goes up past or up to 1 again, a quarter of a pi past that. Okay, so that would be a quarter pi, beyond pi, which would be 5/4 pi. And again, I think more geometrically than I do, well, I guess geometrically is one way to say it, sort of graphically than I do trying to just do through. Now, the other thing is tangent is a periodic function in with a period of pi. So take your pi quarters, add pi to it, and you get, which again is what we did, 4/4 pi, add to 1/4 pi, and you get 5/4 pi. So those are the two consecutive points of intersection. Now, here's what I was saying before. When you divide it by cosine x, in that interval, you divide it by 0. Okay, but we're not interested in the interval. We're just looking for the points of intersection, and those were at pi/4 and 5/4 pi. You're not using this thing anywhere else except to find those points of intersection. So that gives you your limit. Okay, now let's pause for a moment and think, who's on top in that interval? Okay, well, let's pick a point somewhere in the interval, like maybe pi halves. When x is pi halves, sine is 1. When x is pi halves, cosine is 0. So sine's on top, so sine is going to be the f function, and cosine will be the g function. So here we have the integral that we're interested in, the integral going from pi/4 to 5 pi/4 of sine minus cosine. Do you agree with that analysis? And then your width of that interval is going to be dx. Now, they usually put that integrand in parentheses, which does probably make it a little clearer, but I'm so lousy at drawing parentheses, I think we can live with that. So the question now is, what's the antiderivative of sine? Anybody? Antiderivative of sine. Is it that minus cosine? Because derivative of cosine is minus sine, so you'd have to have a minus in front of it to get a plus sign. And what's the antiderivative of cosine x? That is sine x. And you may almost ask yourself, have we done these backwards? Because this is looking awfully negative to me. Well, let's see what you're going from pi fourths to 5 pi fourths. That's supposed to be a pi. It doesn't look like it. 5/4 pi. Okay. That was deadly. Okay. So that's going to be minus the cosine of 5/4 pi. That looked a little better. Minus the sine of 5/4. I think I said 5/4 pi and wrote down pi fourths. Okay. 5/4 pi minus the sine of 5/4 pi. Boy, this is strenuous. Okay. Now we got a minus, but we already got a minus here, so that's minus and minus. That'll be a plus the cosine of pi quarters. I can't get the pen to move. There it goes. Plus, minus and minus again is plus the sine of pi quarters. The lower limit. Okay. Now the question is, what in the world is the cosine of 5/4 pi? Well, let's go back to our unit circle. 1/4 pi, 2/4 pi, 3/4 pi, 4/4 pi, 5/4 pi. You're down in the third quadrant, right? What is cosine in the third quadrant? Negative. And your sine and your cosine at every quarter pi is either plus or minus 1. So that's going to be a minus 1. So it's a minus 1, which would be a 1. And then I just answered the question again. Sine in the third quadrant is also negative, and sine of every quarter pi is 1. So there's another 1. So there's a 1 plus 1. And then you have plus the cosine. I said the plus, but didn't write the 1. Cosine of 1/4 pi. I said that wrong, didn't I? Cosine of pi quarters, I think someone was coming on to correct me, is square root of 2/2. I don't know where my brain is today. Sine of, I was still thinking tangents. Sine of 5/4 pi. All your sines and cosine of your quarter pies are plus or minus root 2/2. So this will be a root 2/2 plus another root 2/2 plus cosine of pi fourths, again, is root 2/2. That's why the tangent is 1, because sine and cosine are the same there, plus another root 2/2. Well, that looks like to me 4 root 2's over 2. Well, 4 over 2 is 2, so it's 2 times root 2, which is something on the order of root 2 is 1.414, so this would be something pretty close to 2.828 or something like that. And they just left it as 2 root 2. Good for them. Any questions? Does that make sense? And every one of those increments, if you had gone from 5/4 pi to 7/4 pi, your curves would have been different, but then the cosine would have been on top. So you would have had to do cosine minus sine. That works. If you went backwards a ways and did from negative 3/4 pi to 1/4 pi, I think that would work. Yeah, that would have been okay too, but again, your cosine would have been on top. Okay, so you could do it infinite number of ways, but you'll get that same answer every time. All right, any questions on that? Okay, how are we doing? We got about 20 minutes. So let's clear the drawings and see if we can get example 4 done. Now, example 4, not only is it in the book here, and those of you who don't have a book, you can actually see example 4 by going to larsoncalculus.com, and there they have an interactive version of this type of an example. They keep saying this type. I think it's the very example, but they may change it a little bit. I don't know why they say this type. But anyway, so you can actually see it and don't have to trust me. So, excuse me. Here it says, find the area of the region between the graphs of f of x is equal to 3x cubed minus x squared minus 10x. 3x cubed, that's a pretty ugly 3. 3x cubed minus, I think it was x squared, wasn't it? Was it minus 10x? Yes, minus 10x. And g of x which is equal to minus x squared plus 2x. Minus x squared plus 2x. Goodness gracious, hold on a moment. Losing my voice again. Okay. I hope I got them written right. Okay. Find the area of the region between the graphs of those two functions. Now, again, you have to find the points of intersection. To find that, you set them equal to each other. So what we got here is 3x cubed. That's an ugly 3. Minus x squared minus 10x set that equal to minus x squared plus 2x. Okay, so what I'm going to do, I'm going to add x squared to both sides here, and guess what? Bing, bing, they both go out. I'm going to subtract 2x from both sides here, and that's going to give me a minus 12x. So what we got, without writing those down, I'm going to get 3x squared, x cubed, see I can't read my writing, minus 12x. When you subtracted everything from this side, that left you a 0. Where would you go from here? Anybody? Those who've been in my class before probably expect this. Some of you who haven't been, don't be shocked. And if this offends anyone, I won't ask it anymore. But when I say what's the F word, what is it? Anyone been in my class before? Factor. Okay? Factor. Okay? So factor out the greatest common factor, which would be 3x. And what does that leave in the first term? X squared minus 4. This is equal to 0. All right. Now obviously the factor 3 will never equal 0, so throw that one away. However, x can be 0, so there's a place where they intersect, x equals 0. But not just there. From this term, you get that x is either or what? Anybody? Plus or minus 2. Because this factor is x plus 2 times x minus 2, and that gave you x equal negative 2 or x equal positive 2. You have 3 points of intersection. So now we have to ask ourselves, who's on top? Okay? So what I'm going to do here, let's take the lower two, minus 2 to 0, pick a number in between, like maybe negative 1. Let's plug a negative 1 in here, and you get a negative 3 minus 1, that would be negative 4, plus 10 would be a plus 6. So at negative 1, F is positive 6. Let's do the G. At negative 1, G is negative 1 minus 2, that's negative 3. Guess what? F's on top between negative 2 and 1. Negative 2 and 0. Let's go over to 1 then and plug in a 1 here. 3 minus 1 would be 2, minus 10 would be negative 12. Plug in a 1 here and you get 1 plus 2 is 1. G's on top between 0 and 2. Okay? So that means we have two different integrals we've got to do. The first integral is going to be from negative 2 to 0. And who did we say was on top there? F was. So that integral is going to be 3x cubed can't write. Okay, there it is. Minus x squared minus a minus x squared, which is plus x squared, and those go to 0 if I'm doing it right. Is that right? I think so. Okay. And then minus 12x. dx. Okay, plus, and this time we've got to put the g on top, and that's when you're going from 0 to 2. With the g on top, you're going to have a minus x squared minus a minus x squared, which is plus, that's going away, and then you're going to have a 2x minus 3x squared, 3x cubed, and 2x minus a minus, that would be plus 12x. Now something seems fishy about this. Let me see if I've done something wrong. Goodness, that's an ugly D. Okay. Oh, my goodness. Here I said, yuck, 2x minus minus, it's just a 12x. This is not there. Okay, sorry about that. I thought these had to be the same, just opposite signs, and that's indeed what they are. Okay. I don't know why I did 2x and then went to doing minus x's. I forgot to subtract the 10x from, negative 10x from the 2x. So that's what we got. I would have written it differently, but it's okay. Let's do the integrals. What's the antiderivative of 3x cubed? Well, take your variable x, up it by 1, making a 4, divide by that 4, but you had a coefficient of 3 here, so that's 3x to the 4th over 4 minus, and this will be the x's squared divided by 2 minus 6x. Evaluate that from negative 2, that's ugly, negative 2 to 0. Okay, plus, this will be the integral from, well, wait, sorry. Okay. Hold on just a second. All right, sorry. Getting awfully dry. Okay. The antiderivative of this is the opposite of this. That would be minus 3/4 x to the 4th. My pen jumped way over there. Okay, 3/4 x to the 4th plus 6x squared and this one is evaluated from 0 to 2. Now, I don't know if you have suspected this yet or not. Okay? Nah. Let me make sure everything is going right. Yeah. If it feels in your heart of hearts these are the same, they sure do seem to be awfully close. But let's just work them out and see. Let's plug in a 0 here. I can do that one. Okay? Both of these are 0. Then let's minus when you plug in a minus 2 here. When you put a minus 2 in here, 2 to the 4th power is 16. Negative 2 to the 4th power is still 16. Divided by 4 would be 4. Times 3 would be 12. And, okay, wait a minute. That's a minus 12, right? No. Yeah, minus 12. And then minus a minus is a plus. And when you square that, it's going to stay a plus. So that would be a plus. 6 times 4 is 24. Okay, and that's going to yield 12. Okay, when you do this side, plug a 2 in there. 2 to the 4th is 16 over 4 is 4 times a negative 3 is a minus 12. And plug a 2 in there, you get 2 squared is 4 times 6 is plus 24. And then when you plug zeros in, you get nothing, okay, 0. So this gives you a 12, and 12 plus 12 is 24. So sure enough, those are the same values under each curve. What's bizarre about it, they don't look at all the same. And again, there's the graph. If I can get it, there's the graph. And they don't look the same, but you could be convinced they have the same areas. Okay. But if you go to calculus, larsoncalculus.com, you can see it all worked out there. And the answer is 24. Now, if you had tried to do minus 2 to 2, and you just arbitrarily chose one of those to be greater than the other, okay, which they're not, okay, I mean, they're not consistently, you wind up with an area of 0 because half of that is a positive and half is a negative, and you add those two together and you get 0. That's why when you did them separately, they exactly doubled. Okay. Now, they have a blurb in the book. Let's see, we've got 5 minutes. When the graph of a function of y has a boundary, is a boundary on a region, it's often convenient to use representative rectangles that are horizontal and you do your dy's in. And that's a perfectly legitimate thing to do. Except now you're no longer talking about top and bottom because you're horizontal. You're talking about right to left. So it's always right hand to left hand. That's going to be your length. The length of the rectangle, the height is going to be your delta x. Or if you want to call this the length and that's the width, length is going to be right to left, right minus left, times your delta y. Okay. So that's what they do at the bottom of page 447. I'm really surprised they did not include that on the slide set. And the reason they didn't is they wanted me to have to draw those curves, and I'm not about to. So hopefully you're okay with me with that explanation. Now I'm going to clear the drawing out. I don't know if we're going to have time to finish the problem or not, but let's at least get it started. Okay? We've got 4 minutes left. You know, I don't guess it's worth starting. Let's start next time with example 5. Okay? So let me mark my place here. And let's go to, oh, we are 2 examples from being through with this section. Okay? So chapter 7 I think is going to go a little faster than at least portions of it will, than chapter 5 did. Okay, so homework exercises in 7.1. Do any of the odds 5 through 9. They're all at Calc Chat. 7's at Calc View. Do either 11 or 13. They're both at Calc Chat. 11's at Calc View. Do any of the odds 15 to 27. They're all at Calc Chat. 17's at Calc View. And do any of the odds, do 29 is both at Calc Chat and Calc View. Okay, trying to see. Okay. Do any of the odds 31 to 35, they're all at Calc Chat. And 37 to 41, they're all at Calc Chat with 37 at Calc View. 43 or 45, they're both at Calc Chat. And 47 or 49, they're both at Calc Chat. 59 should be at Calc Chat. We'll stop there now and we'll pick up the rest of those next time. Okay? So, any questions on anything that we've done today? Okay, what's that?
I had a question about, you know, when it's going from the bottom and you had to determine which one was larger. I was trying to understand that process.
Okay, who's on top? Is that what you mean?
Yes, sir.
Okay. Okay, now I do it sort of simple-mindedly. If you have one graph that's doing like this, these are supposed to be smooth curves, and the other one's doing something like this. Okay, that's sort of what you're talking about, right? We wound up with 3 points of intersection. One here, and you know they meet at those points. Those are the points of intersection. That's when we set the two functions equal to each other. Okay, and this has an x value, that has an x value, that has an x value. What I do, sort of simple-mindedly here, is pick a value of x somewhere in between that x value and that one. The one that we were doing was -2 to 0. So I chose -1. And if this was my f function here, and this was the g here, I do f at -1 and g at -1. See which is a larger value. And that tells you f is between that 0 and that 0. In other words, where the difference is 0, f is always on top. But if you did the same thing here, and this happened to be in our problem at 0, oh goodness, I'm not even touching that, 0 to 2, so I just chose 1 here, and plug in here, and I got g being greater here when I plugged in 1. When I plug in 1 for f, it was less. So I knew g was on top, so I do g minus f on that one. F minus g here, because your little rectangle here goes from the upper to the lower. So it's g minus f is your height, f minus g is your height here, whereas here, oh, that's supposed to be a rectangle. That's a pretty ugly rectangle. Here it's g minus f, because you always do the one on top minus the one on bottom. Does that help at all?
Yes, sir. It helps. Thank you.
Okay, good. Any other questions? That was a great question, by the way. I know I sort of blew past it. Any other questions? All right. Guess what? Today we're ending right on time. Is that, well, a minute late, but no extra charge. Okay, so I'm going to stop the share. Work on your test. You don't have to turn me in any homework exercises anymore. I want you working on the test. I do want you working homework exercises, but I'd rather you send me stuff tests. Now, if you want to send me some, especially if you have any, you're having difficulty getting the answers, please send those. But other than that, you don't have to send stuff until you send the test. And that will be enough, because that's an assignment. Whenever you get it done, send it to me. Okay. Any questions? Okay, I'm stopping the sharing now, and I'm ending the meeting now, so we'll see you on Monday. Have a good weekend. Of course, working on calculus will make it good, right? Good deal. Okay.